Dear students, let's discuss this session number 23 on industrial metallurgy. Let me show the various topics that we'll cover in this session. In the last session, we had discussed actually what is meant by coring. And now in this session, we'll discuss as to what are the various factors, conditions which affect coring, means which would promote coring or which can reduce the extent of coring. And then very briefly, we would tell you that what is the remedy when coring is there in a type 1 alloy casting. How do we actually reduce it? Means we'll not discuss it in detail, but we'll give you a glimpse, and then in the next session we'll take up it in more detail as to how coring can be, the effects of coring can be reduced or eliminated. Okay, so let's here discuss that what are the various factors which affect the coring phenomenon. Now, if you remember in the last session, we had said that whensoever for a type 1 alloy system, non-equilibrium cooling will be done, rapid cooling would be done. One of the problems would be that the rate of solidification would be very fast, and the rate of diffusion, which is dependent upon time, would be less. And because of this faster rate of solidification as compared to the rate of diffusion, when you look into the final microstructure that is obtained in the alloy, you will see that a cold type of a structure has got formed. Cold in the sense that there would be regions in the center of the grain which would be rich in one type of constituent element, and that would generally be the high melting point constituent element. And the regions which are close to the grain boundaries, the outer fringes of the dendrites, the outer fringes of the grains, they would be relatively rich in the other constituent element of the alloy, and this would be generally the low melting point element constituent of the alloy. So what will happen because of non-equilibrium cooling will be that the final alloy that has been obtained under room temperature conditions is not truly an alloy, because it has got great composition gradient in it. And because of that, uh, okay, we'll see how do we get rid of that. But first we should see what would promote coring, right? So that we can keep these factors in mind, and we can then reduce the extent of coring that can happen in our alloy system which is being prepared and is being cooled. So the first and the foremost factor is the rate of cooling. Faster is the rate of cooling, more would be the departure between the rates of solidification and the rate of diffusion, and hence more would be the extent of coring. So here in this diagram, we have tried to show that if you were following equilibrium cooling rate, then the chemical composition of the solid phase varies along this brown line, this equilibrium solidus line. But if you start doing non-equilibrium cooling, the solid phases chemical composition is not shown by the equilibrium solidus line, but a line depressed below it. So in the last session we had seen that if we are following some fast rate of cooling, there would be a departure and a new effective solidus line would be obtained. Now students, for the same alloy, if the rate of cooling is even faster than the rate of cooling, the non-equilibrium rate of cooling for which this non-equilibrium solidus line was obtained, if the rate of cooling is even faster than this, then there would be more departure between the equilibrium solidus line and the effective solidus line, and then the curve may be this. And if you go beyond uh, a, a cooling rate which is even faster than these two, then for that the solidus line, the effective or the depressed solidus line would come like this. So the first factor which promotes coring is the fact that whenever you will depart from the equilibrium cooling rate, whenever you will do non-cooling rate, whenever your rate of cooling would be fast, the time available for diffusion would be less and there would be more coring. Second is the solidification range. Now if somebody asks you that if for a given system, like here we have the copper nickel system. I have a 20% 20% nickel and 80% alloy, and or I have the 60% nickel or 35% alloy. These alloys are belonging to the same alloy series, the copper nickel alloy series. Now if there is non-equilibrium cooling and the rate of cooling is the same, then for two different alloys, is the extent of coring going to be the same? The answer is no. Coring for a given rate of cooling depends upon the solidification range. Means if I have taken an alloy whose solidification is very big, and now I take another alloy whose solidification is only this or is only this, then for a given rate of cooling, for a given rate of non-equilibrium cooling, the alloy whose freezing range is larger, the departure between the equilibrium solidus and the non-equilibrium solidus line would always be greater. Means for any alloy for a given rate of cooling which has got a larger freezing range than another alloy which has got a smaller freezing range, the alloy whose freezing range is larger will have more extent of coring for a given cooling rate as compared to another alloy with a smaller freezing range. Then the same I would have written on the next slide. Okay, this is this. Then third point, that if the non-equilibrium rate of cooling is the same, and then the solidification range is also the same. For example, if I take two alloys whose solidification range is the same. See, this example that I have taken, this was for point number 2, solidification range. So clearly, if you have an alloy whose solidification range is given by temperature difference Ta minus Tb, and there is another alloy whose solidification range is given by temperature difference Tc minus Td, because for the same rate of cooling whatsoever, this or this, whatsoever is followed for these two alloys, for a given same rate of cooling, this alloy would show more coring. Then we come to the third point, that if the rate of cooling is the same and even this freezing range is the same, the difference between the solidus. So if I had an alloy somewhere over here, it is having a solidification range of similar to what this Ta minus Tb is having. So if there are two alloys whose rate of cooling is the same, whose solidification range, that is difference between the liquidus and the solidus temperature, is the same, then in that, whether coring would be the same? No. See, coring depends upon composition gradient. See, what does diffusion depend upon? Students, diffusion, the driving force behind diffusion is composition gradient. But only composition gradient existing does not lead to confusion. If you have an alloy which has got a great composition gradient in it, but that is lying at the room temperature, diffusion wants to happen but will not be able to happen. So the primary driving force for diffusion to exist or to have a wish to happen is the composition. The very reason for diffusion to happen is composition gradient. But just having composition gradient is not sufficient. Diffusion, in order to have to occur, needs a proper temperature. Not only temperature, it needs another equally important point, that's time. So if composition gradient exists and the material system is present at a suitable temperature where diffusion can occur, and at that, with that composition gradient and at that temperature, if you are giving sufficient of time to the materials system, then only diffusion would happen. So if you have two alloys with the same freezing range and you are subjecting them to some same cooling rate, then the alloy whose same freezing range is lying in the upper temperature band. See, Ta minus Tb might be same to another alloy with say Tx minus Ty, but Ta minus Tb is lying in a higher temperature band as compared to another alloy somewhere over here. So here diffusion would be more with the same rate of cooling. So this alloy, which is at a lower temperature range, even with the same solidification range, this alloy somewhere over here will show higher amount of coring. Or in other words, alloy with the same rate of cooling and with the same solidification range, because it is lying at a higher temperature band, will show more diffusion and hence less scoring. Apart from these factors, even if all these three factors that I've listed in the beginning, these three factors, even if these three factors are the same, a lot would depend upon the type of material system under question. So for example, if you have taken a copper nickel alloy and you have taken a, say, lead tin alloy, right? And then if the rate of cooling, if the solidification range, if the temperature values of the solidification range all are same, whether the extent of coring in the copper nickel system and in the lead tin system be the same? No. See, the amount of diffusion apart from these factors also depends upon the nature of the pair of elements who have to show diffusion with each other. For example, in case of copper nickel system, when there is a composition gradient and the diffusion process realizes that there are more of nickel atoms in the core of the grains and there are more of copper atoms in the regions close to the grain boundaries, diffusion is taking place between what? Excess of nickel atoms are moving towards the outer peripheral areas. Copper atoms from the outer peripheral areas, grain boundaries areas, are moving towards the core of the grains where they are deficient. So diffusion is taking place between two unlike atoms of two unlike elements. Their atomic size, their other nature is different. So even for two different material systems, if these first three factors are the same, the extent of coring might be different because diffusivity between different pair of atoms are different. So diffusivity, any pair of elements in which diffusivity is more, diffusion would be more, and hence coring would be less if these first three factors are taken as the same. So students, these were the factors. Then how do we then get rid of coring? See, or how do we homogenize? Because there is a composition gradient, there is non-homogeneity. How do we homogenize? Generally, it is said that the time required to homogenize a cored alloy depends upon the grain size. Grain size fine, coring would be eliminated quickly. If the grain size is coarse, a lot of diffusion has to be done, and then it would take time. How much of coring is there? Larger is the amount of coring, more the time it would take, and vice versa. Temperature of diffusion, at higher temperatures coring would get eliminated soon. Diffusion rates, etc., etc. The time to homogenize can be reduced. See, there is a treatment that we'll discuss. It is homogenization annealing treatment through which coring is eliminated. And if you still want to reduce the time which is taken for homogenization annealing, you can initially do plastic deformation of your alloy or casting. That will reduce the grain size, and reduced grain size, time taken to diffuse would be less. So the total time that would be taken for homogenized annealing after, if you take a cold worked core casting, homogenization annealing would take less of time. I hope you understood all the things that we have covered in this session. Thanks for your patience.